Black holes bend time itself in ways we can barely imagine when we think about them. They create regions where clocks slow down and eventually stop completely at the edge. Light cannot escape from within their boundaries, no matter how it tries. Space twists into shapes that seem impossible to our everyday thinking. Tonight, we explore 9 layers of this mysterious cosmic fountain of time. Each layer shows different effects on how time flows and behaves. We start far from the black hole, where effects are gentle. Then move closer through each region as we descend deeper inward. Each section reveals new physics about time and its strange behavior. Simple words and clear explanations will guide us through this journey. No complex jargon, just pure understanding delivered in a gentle way. Let's begin this slow journey through the fabric of space-time together. Gravity affects time in ways that we can actually measure with precise instruments today. Einstein proved this over a century ago with his revolutionary theories. His general relativity equations show exactly how mass curves space-time in all directions. This curvature makes time run at different rates depending on location. Near massive objects like planets or stars, time slows down in measurable ways. Far from mass and empty space, time runs faster by comparison. This effect is called gravitational time dilation, and it happens everywhere constantly. It's real, measurable, and affects everything in the universe without exception. Black holes have extreme mass concentrated into incredibly tiny spaces around them. So they create the most extreme time dilation effects possible anywhere. Even far from a black hole's center, where gravity seems weak. Time runs slower than it does in completely empty space regions. This region extends outward for great distances, depending on the hole's mass. Scientists call this the slow time shell because time stretches here gently. It's the first layer where these strange effects become noticeable to observers. GPS satellites actually experience this effect every single day they orbit above us. They circle Earth at high altitude positions about 20,000 kilometers up. Time runs faster up there than it does down on Earth's surface. About 38 microseconds faster each day when we measure it carefully. Engineers must correct for this time difference in the satellite programming. Otherwise, GPS coordinates would drift off by kilometers very rapidly over time. This proves that time dilation is absolutely real and must be accounted for. Near a black hole, the effects become much stronger than around Earth. A clock placed near a black hole will tick slower and slower, compared to an identical clock sitting far away in empty space regions. The difference grows larger and larger as you approach closer to the hole. At the slow time shell's inner edge, closest to the black hole, time runs noticeably slower than in the regions outside this boundary completely. Let's use specific numbers to help understand this better and more clearly. Say you're positioned 1,000 kilometers away from the event horizon's edge. Your clock would tick at roughly 90% of its normal speed. An outside observer watching from far away would see your clock slowing down. But you yourself would experience time flowing normally from your own perspective. Your heartbeat would feel completely normal to you without any strange sensations. Your thoughts would proceed at their usual pace inside your mind naturally. Only by comparing clocks would anyone notice the time difference between locations. Move closer to 500 kilometers from the horizon's edge now instead. Time runs at about 80% of normal speed at this distance. Closer still to 200 kilometers away from the horizon exactly measured. Time drops down to roughly 60% of normal speed there. The closer you get to the hole, the slower time flows. This gradient of increasing slowness creates the slow time shell's layered structure. This shell affects absolutely everything that passes through it, without exception at all. Starlight crossing through this region gets affected in noticeable and measurable ways. The light's frequency shifts toward the red end of the spectrum gradually. This red shift tells astronomers important information about the time dilation happening there. We measure the redshift carefully from distant stars near black holes today. This reveals the black hole's mass and our distance from it accurately. Matter falling through this shell also appears to slow down visibly to observers. Gas spiraling inward toward the black hole heats up from friction between particles. Friction between gas particles creates tremendous temperatures that keep rising higher. This superheated gas emits powerful X-rays that we can detect from Earth. The X-ray emission varies over time in patterns we can measure carefully. These variations clearly show time dilation effects happening in that region around holes. Stars sometimes orbit through this region regularly in the centers of galaxies everywhere. Their orbital periods get measurably affected by the time dilation present there. An orbit that would normally take exactly 1 year to complete fully might take 14 months when measured by clocks outside the shell's influence. The star itself experiences completely normal time during its entire orbital journey. But external clocks, positioned far away, measure much longer time periods passing. This difference between measurements confirms time dilation predictions made by Einstein's theory. The shell also affects orbital mechanics in subtle but important ways throughout. Mercury's orbit around our Sun shows a slow precession over very long times. The orbit's orientation rotates gradually over centuries of careful astronomical observation. Newton's gravity theory couldn't fully explain this precession amount correctly at all. Einstein's relativity predicted the exact precession amount that astronomers actually observed perfectly. Near black holes, this precession effect is much stronger and more dramatic. Orbits rotate faster due to the much stronger space-time curvature present there. The innermost stable circular orbit exists somewhere in this shell's inner regions today. Astronomers abbreviate this special distance as ISCO in their scientific papers regularly. This marks the location where stable circular orbits become completely impossible closer in. Closer than ISCO, matter absolutely must spiral inward without any other option. It cannot maintain circular orbits anymore at any distance closer than this. The ISCO location depends specifically on the black hole's spin rate measured. Non-spinning black holes have their ISCO at exactly 6 times the Schwarzschild radius. This radius is measured outward from the black hole's geometric center point. Spinning black holes have completely different ISCO positions than non-spinning ones do entirely. For maximum possible spin rate, the ISCO moves much closer inward dramatically. as close as 1.2 times the radius for maximally spinning holes. This large difference reveals important information about how fast black holes rotate. By measuring carefully where the ISECO occurs in our detailed observations today, we can determine how fast that particular black hole spins quite accurately. The slow time shell creates gravitational lensing effects that bend light dramatically around. Light bends as it passes around the black hole's concentrated mass distribution nearby. This bending magnifies and distorts background objects positioned behind the black hole completely. We see multiple distorted images of distant stars at different positions simultaneously. Or we observe stretched arcs of light curving around the black hole's position. This gravitational lensing reveals the black hole's total mass very precisely through measurements. Einstein first predicted gravitational lensing would occur back in 1915 originally. But this prediction wasn't confirmed observationally until the 1919 solar eclipse expedition. Arthur Eddington carefully measured starlight bending near the sun during totality precisely then. This conclusively proved that Einstein's new theory was correct about gravity's nature. Near black holes, the lensing becomes much more extreme and dramatic visually, creating spectacular visual effects that we can now photograph directly with telescopes. The slow time shell extends very far outward from the black hole's center. For supermassive black holes containing millions or billions of solar masses total, the shell can extend outward across many light years of distance into space. Even at these enormous distances from the hole, time dilation still exists measurably. Though the effects become quite small, they're definitely still present and real. Modern astronomical instruments can detect even these tiny differences accurately through careful measurement. This shell naturally regulates the matter accretion rates importantly for black hole feeding. Matter falling inward must pass through this shell on its journey downward. The time dilation effect creates a natural bottleneck that slows things down. Matter simply can't fall inward faster than the physics of time allows. This keeps the accretion happening at steady and predictable rates over time, preventing the black hole from trying to feed too rapidly all at once. If matter could fall in without any time dilation slowing it down first, the black hole would consume everything much too quickly in violent bursts. It would temporarily choke on the infalling matter coming in too fast, then violently spit some material back outward in explosive outbursts of energy. But time dilation smooths this entire feeding process out naturally and gently, creating steady and long-term accretion instead of chaotic and violent feeding patterns. Accretion disks form naturally in this region and remain quite stable over time. The disk consists of matter slowly spiraling inward in organized patterns gradually. It heats up tremendously through friction between countless particles constantly colliding together. Inner regions closer to the hole are much hotter than outer regions. Temperatures can reach many millions of degrees in the innermost disk regions. This tremendous heat makes accretion disks incredibly bright sources of radiation we observe. We observe these accretion disks around many black holes throughout our galaxy today. They emit radiation across the entire electromagnetic spectrum without any gaps at all. Radio waves from cooler outer regions, infrared from warm middle sections nearby. visible light that our eyes could see if we were close enough. Ultraviolet radiation from hotter inner regions closer to the black hole itself. X-rays and gamma rays streaming from the very hottest regions right near the hole. By carefully studying these emissions at all wavelengths, we learn about disk conditions, temperature distributions, particle density, velocity patterns, all revealed through detailed spectrum analysis. The slow-time shell also affects fundamental particle physics in interesting ways. High-energy particles moving through this region experience significant time dilation effects too. This actually changes their natural decay rates in measurable and significant ways. Particles that normally decay very quickly in laboratory conditions here on Earth live noticeably longer when moving at high speed near black holes instead. This lifetime extension allows different particle interactions to become possible there. Interactions that would never happen in normal space, where particles decay faster. Cosmic rays entering this region get affected in similar ways to other particles. These incredibly high-energy particles come streaming in from deep space constantly when they pass near black holes on their journeys through space. Their trajectories bend significantly due to the strong gravity's pull on them, and their internal clocks slow down measurably from time dilation effects present. This creates unique, observable signatures that we can detect remotely with our instruments. The shell's time gradient is perfectly smooth, not abrupt anywhere in the region. Time dilation increases gradually and continuously as you approach inward toward the hole. There's absolutely no sharp boundary where effects suddenly start happening all at once. It's a continuous smooth change from normal time to slower time rates. This smoothness comes directly from gravity's fundamental mathematical nature in Einstein's equations. Gravitational fields simply don't have sharp edges anywhere in their natural structure. Different black holes create shells with different strengths depending on their mass. Stellar mass black holes, containing just a few times our Sun's mass total, create very strong shells close in, but with quite limited spatial extent. Supermassive black holes, containing millions or billions of solar masses instead, create weaker, but much more spatially extensive shells spreading far outward. Both types follow exactly the same underlying physics principles without any difference. Just completely different scales and magnitudes of the same fundamental effects occurring. The temperature of the slow-time shell itself is extremely cold everywhere. Space around black holes is nearly perfect vacuum with almost no matter. Without any matter present, there's nothing there to actually have temperature. The cosmic microwave background radiation does fill this region, though uniformly, at about 3 degrees above absolute zero temperature throughout all space. This incredibly faint radiation pervades all of space everywhere uniformly without exception. The shell's properties change over time, but extremely slowly over cosmic ages, as the black hole gradually gains mass from ongoing accretion of matter. The shell grows steadily larger and stronger in its effects gradually, as the black hole slowly loses mass from Hawking radiation evaporation instead. The shell shrinks and weakens over time in the opposite direction. These changes take many billions of years to become noticeable to observers. Scientists study this shell using multiple complementary methods available today with technology. direct observation of individual stars orbiting around supermassive black holes in galactic centers, detailed spectroscopy of accretion disk emissions coming from actively feeding black holes, gravitational wave detections from pairs of black holes merging together violently. Each different method reveals different aspects of the shell's detailed properties clearly. Together, they build a complete picture of how this region behaves. The slow time shell proves that Einstein's relativity is fundamentally correct about nature. Every single measurement ever made confirms Einstein's theoretical predictions precisely and accurately. No deviations whatsoever have been found, despite decades of intensive searching. This gives scientists tremendous confidence in our understanding of this region completely. The slow time shell is now very well understood scientifically by astronomers today. At exactly 1.5 times the Schwarzschild radius distance from center, something truly remarkable happens to light that passes through this special location. Light can actually orbit the black hole in perfect circles going around endlessly without ever escaping outward or falling inward fatally. This special distance is called the photon sphere by physicists studying it. It's a unique region with truly bizarre and fascinating properties unlike anywhere else. The photon sphere exists at a precisely fixed radius that never changes position. For non-spinning black holes, it's exactly calculated from mathematical equations describing gravity. At precisely 3 times the gravitational radius measured outward from the center. This radius depends only on the black hole's total mass and nothing else. Bigger black holes naturally have proportionally larger photon spheres around them correspondingly. Smaller black holes have tighter and more compact spheres closer to their centers. Light normally travels in perfectly straight lines through empty space without deviation. But gravity significantly curves the space that light actually travels through on its path. So light simply follows the curved space's underlying geometry without any choice. Near black holes, the space-time curvature becomes extreme enough in strength finally. That light's natural path bends all the way around into circular orbits. This unique possibility creates the photon sphere's most defining characteristic completely. Photons are the fundamental particles of light that carry electromagnetic energy without mass. They always travel at exactly light speed through space without any exception. Never faster, never slower, always at constant speed no matter what. But their direction of travel can definitely change from gravity's influence on them. The photon sphere is precisely where space-time curvature allows and enables. Perfectly circular orbits at exactly light speed to be maintained there. These circular orbits are inherently unstable by their very fundamental nature though. Any small perturbation or disturbance knocks the photons out of orbit completely. If bumped even slightly inward toward the hull, photons fall in irreversibly. If bumped even slightly outward away from the hull, they escape successfully. Only at exactly the photon sphere radius position can photons possibly maintain circular orbital motion successfully for any length of time at all. This inherent instability means photons never accumulate there in large numbers together. The photon sphere region isn't glowing bright or visible to observers at all. It's constantly being refreshed with brand new photons arriving from various directions, while old photons already there get knocked out of orbit continuously and leave. The sphere exists as a possibility region in space-time where orbits can occur, not as any kind of physical structure you could actually see directly. Light can complete multiple full orbits before finally escaping outward to freedom. Some individual photons circle around once, then immediately fly away successfully afterward. Others might circle twice around before finally escaping outward into space beyond. Some circle many times before eventually leaving the region at last. Each creates a time-delayed image of itself, arriving at different times, arriving at distant observers at different moments, staggered apart in time. This creates a fascinating echo effect with the light itself traveling. One single source can produce multiple images arriving in sequence over time. Each image shows the exact same event, but delayed by different amounts. The delay depends specifically on how many complete orbits around the hole. The light successfully completed before finally escaping outward to observers successfully. Scientists call this the gravitational lensing echo effect in their research papers. The photon sphere acts as a powerful gravitational lens, bending light significantly, magnifying and dramatically distorting light passing near it from behind the hole. Background objects like distant stars get stretched and distorted significantly into arcs, creating bright rings and arcs of light around the black hole's silhouette. These Einstein rings were predicted, theoretically, by relativity decades before being observed. And we've now observed them around many different black holes in actual images. The famous black hole image, released in 2019 by astronomers worldwide, showed a bright glowing ring of light around a dark central shadow. That bright ring traces very close to the photon sphere's actual location, though the ring is actually just slightly outside the sphere itself technically. The image beautifully confirmed predictions that theorists made many decades earlier, proving conclusively that our understanding of photon spheres is fundamentally correct. Different wavelengths of light behave identically at the photon sphere's location. Radio waves, visible light, and gamma rays all orbit at the same radius, at exactly the same distance from the center, regardless of their wavelength. Because the photon sphere location depends only on space-time geometry alone, not on the light's energy or frequency or any other characteristics. This beautiful universality confirms relativistic predictions accurately and demonstrates their correctness. Spinning black holes have significantly more complex photon sphere structures than simple ones. Instead of one single sphere, there are actually two distinct spheres present. One sphere for light orbiting in the same direction as the spin. Another separate sphere for light orbiting against the spin direction instead. Scientists call these prograde and retrograde orbits in their technical descriptions. They occur at measurably different radii measured from the black hole's center. The prograde photon sphere sits noticeably closer inward toward the black hole. Light moving with the spin direction experiences frame dragging effects helping it. This dragging effect helps maintain circular orbits at smaller radii than otherwise. The retrograde sphere sits farther outward away from the center instead. Light moving against the spin direction fights against frame, dragging continuously. requiring a larger radius position to successfully maintain circular orbital motion there. Between these two distinct photon spheres exists an interesting intermediate region, where light can orbit in much more complex patterns than simple circles. Not simple perfect circles, but spirals and wobbles and complex trajectories instead. Eventually, these complex paths spiral inward or escape outward completely from the region. Scientists call this the photon zone rather than sphere in technical papers. It's thicker than a simple sphere, more like a shell structure instead. The photon sphere significantly affects the black hole shadow we observe in images. The shadow is the dark circular region in the center of pictures, where absolutely no light can escape from within its boundaries ever. The shadow's edge corresponds roughly to the photon sphere's position approximately. Light just outside the sphere can still escape after orbiting around. Light just inside falls inevitably into the black hole without any escape possible. The shadow's size depends on the black hole's physical properties we're observing. Total mass determines the overall scale of the shadow clearly and directly. Spin rate affects the shadow's shape and asymmetry that we measure carefully. By measuring shadows precisely from detailed observations with advanced telescopes today, we can determine the black hole's mass and spin rate quite accurately. The photon sphere temporarily stores information, but only very briefly in time. Light carrying signals orbits around before eventually escaping outward to observers. This creates a measurable delay in signal transmission through the region, like a traffic circle that delays cars passing through it temporarily. The delay depends on how many orbits were completed before escape. This delay affects the timing of signals that observers receive from sources. Pulses of light get smeared out temporally into longer duration signals. A short flash becomes stretched into a much longer duration event. From multiple orbit delays, all adding up together in the final signal. This characteristic helps astronomers identify photon sphere effects clearly and definitively. In observations of emissions coming from black hole accretion disk regions nearby. Photon spheres also create multiple images of objects positioned behind the hole. A single distant star behind a black hole appears at multiple locations, at several different positions around the black hole's edge in our images. Each image comes from light taking different paths around the hole. Some photons going left, some right, some orbiting multiple complete times, all arriving at the observer from completely different directions in space. These multiple images usually have different brightnesses from each other clearly. Images from light that orbited more times are typically much dimmer, because more photons get lost during each additional orbit around the hole. Also, those photons are older by the time they finally escape. Coming from earlier in the source's history than the direct path photons, the photon sphere can't trap light permanently for infinite time ever, because the orbits are inherently unstable, as described earlier in detail. Eventually, every single photon either falls inward or escapes outward successfully. Nothing stays at the photon sphere location for very long time periods. It's a transient region, constantly changing membership of which photons are present. But the sphere itself remains a permanent structure at fixed location always. As long as the black hole exists there, the photon sphere persists. New photons constantly arrive to replace old ones that have departed. The sphere persists even though individual photons come and go rapidly. It's like a waterfall where water constantly changes, but the fall remains. The photon sphere is similar in this fundamental way exactly. The sphere affects how we image black holes with radio telescope arrays. The Event Horizon Telescope used this effect to create those famous images. By carefully analyzing light from the photon sphere region specifically in detail, they reconstructed the black hole's shadow and surrounding bright ring clearly. This technique will help us image many more black holes precisely. Future observations will study photon spheres in much greater detail than possible, measuring how they change over time from black hole spin variations, detecting differences between theory and observation, if any exist at all. Each measurement helps refine our understanding of extreme gravity's effects. The photon sphere remains a fascinating laboratory for testing relativity's predictions. The event horizon is the most famous feature of any black hole. It's the boundary that defines the black hole itself, fundamentally and completely. This is the point of no return from which nothing can ever escape. Not matter, not light, not information, absolutely nothing whatsoever gets back out. Once anything crosses this boundary inward, it belongs to the black hole forever. This makes the event horizon the most dramatic boundary in all of physics. The horizon forms at a specific radius determined by the black hole's mass. For non-spinning black holes, we call this the Schwarzschild radius precisely and exactly. The radius equals 2 times the gravitational constant times the mass total, divided by the speed of light squared in Einstein's famous equations. This gives a direct relationship between mass and horizon size, always proportionally. More massive black holes have proportionally larger horizons around them correspondingly today. For a black hole with our sun's mass, the horizon radius equals 3 kilometers. This means you'd have to crush the sun down to 6 kilometers across before it would form an event horizon and become a black hole. For Earth, the horizon radius would be just 9 millimeters across, about the size of a small marble you could hold easily. These numbers show how incredibly dense black holes actually are inside. The horizon is not a physical surface you could touch or stand on. There's no wall there, no barrier made of any kind of matter. It's purely a mathematical surface in space-time, where properties change dramatically. A boundary where the geometry of space-time itself becomes qualitatively different fundamentally. Outside the horizon, escape is difficult, but still technically possible theoretically always. Inside the horizon, escape becomes absolutely impossible under any circumstances whatsoever completely. Time behaves very strangely at the event horizon's location in space precisely. From an outside observer's perspective, watching from far away safely somewhere, time appears to stop completely at the horizon's edge without continuing forward. Objects falling toward the horizon appear to slow down progressively and continuously, getting slower and slower as they approach closer to that boundary, eventually appearing to freeze completely at the horizon's edge without crossing. But from the perspective of something actually falling through the horizon itself, time continues flowing forward completely normally without any strange sensations at all. The horizon is crossed in finite time from the falling object's perspective. No freezing, no slowing, no strange effects felt whatsoever by the infalling object. It simply passes through the horizon and continues falling inward towards center. This dramatic difference between perspectives is one of relativity's strangest predictions completely. This creates what scientists call the frozen star appearance to outside observers. Everything that ever fell into the black hole appears frozen at the horizon, creating a kind of ghostly image preserved there eternally without fading. Though the light from these frozen images redshifts and dims over time, eventually becoming too faint to detect with any instruments available today. But mathematically, the information remains there encoded on the horizon's surface structure. The horizon acts as a one-way membrane, allowing things through in one direction. Matter and light can cross inward through the horizon without any resistance. But absolutely nothing can cross outward through the horizon ever under any conditions. This one-way property makes the horizon unique in all of physics completely. No other boundary in nature works quite this way at all. Inside the horizon, space-time has radically different properties than outside it completely. Space and time actually swap roles in a very real mathematical sense. What was a direction in space becomes a direction in time instead. What was forward in time becomes inward in space toward the center. This role reversal means that moving inward becomes as inevitable as moving forward. In time normally outside the horizon, in normal space everywhere else. You can't stop moving forward in time, normally in everyday life experiences. Similarly, inside a horizon, you can't stop moving inward towards center. It's not a force pushing you, it's the structure of space-time itself. Time points inward inside the horizon, so everything must follow it inward. This makes reaching the center absolutely inevitable once you've crossed the horizon. The horizon's size depends on the black hole's mass and spin rate. For spinning black holes, the horizon becomes slightly smaller than non-spinning ones. The fastest possible spin reduces the horizon to about half size. This happens because rotation adds energy that contributes to the gravity field, making the black hole more compact than a non-spinning one of same mass. The horizon's shape also changes with spin rate significantly and measurably today. Non-spinning black holes have perfectly spherical horizons, symmetrical in all directions. Spinning black holes have oblate horizons flattened at the poles significantly, bulging outward at the equator from centrifugal effects of the rotation. The faster the spin, the more pronounced this flattening becomes over time. The horizon emits very faint radiation discovered by Stephen Hawking theoretically decades ago. This Hawking radiation comes from quantum effects right at the horizon's edge. Particle pairs spontaneously form from vacuum fluctuations everywhere in space constantly. Normally, they annihilate immediately, but at the horizon something different happens. One particle falls in while its partner escapes outward successfully instead. The escaped particle becomes Hawking radiation we can theoretically detect someday perhaps. This radiation is extremely weak for any black hole we could observe. For stellar mass, black holes, the temperature is billionths of a degree. Far colder than the cosmic microwave background, filling space everywhere around. So these black holes actually absorb more radiation than they emit currently. Only incredibly tiny black holes would emit significantly, but none exist naturally. Primordial black holes from the early universe might emit noticeably if they exist. Over incredibly long timescales, Hawking radiation makes black holes evaporate completely away. The black hole loses mass gradually as radiation escapes, carrying energy away. This makes the black hole shrink slowly over trillions upon trillions of years. Eventually, it would evaporate completely, leaving nothing behind at all theoretically. Though this takes far longer than the current age of the universe. The horizon stores information in ways we don't fully understand yet completely. The information paradox asks, what happens to information falling into black holes? Quantum mechanics says information can never be destroyed under any circumstances ever. But black holes seem to destroy everything that falls in without trace. This contradiction between quantum mechanics and relativity remains unsolved today completely. Some scientists think information gets encoded on the horizon's surface structure somehow. In microscopic details we can't observe, but that exist mathematically nonetheless. This holographic principle suggests the horizon acts like a two-dimensional computer screen, storing three-dimensional information about everything that fell in over time past. This idea is still being developed and tested through theoretical calculations. The horizon marks the black hole's size for all practical purposes we observe. When we say a black hole is certain size, we mean its horizon. Everything interesting happens at or outside the horizon where we can observe. Inside remains forever hidden from view, behind this impenetrable boundary completely. This makes the horizon the defining feature of black holes, fundamentally for science. Different types of black holes have different horizon sizes, obviously and measurably. Stellar mass black holes from collapsed stars have horizons kilometers across only. Supermassive black holes in galaxy centers have horizons millions of kilometers across. The largest known black holes have horizons that could fit several solar systems. Inside comfortably, with room to spare even for outer planets to orbit. The horizon also defines what we mean by black hole mass precisely. Mass is measured by the horizon's size using Einstein's equations directly. Bigger horizon means more mass proportionally, in direct relationship always without exception. We can't see inside to weigh the contents directly, obviously. So the horizon size is how we measure black hole masses. Crossing the horizon is called spaghettification, informally by physicists describing it colorfully. Because tidal forces stretch objects into long, thin shapes like spaghetti noodles. The gravity at your feet is stronger than at your head. This difference stretches you vertically while squeezing you horizontally, simultaneously together. For small black holes, this happens before reaching the horizon's edge. For supermassive black holes, you could cross the horizon intact before being torn. The event horizon represents a fundamental limit in our universe's structure completely, a boundary beyond which we can never see or receive information from. It's the ultimate cosmic sensor hiding what happens inside from outside view. This makes black holes both fascinating and frustrating to study scientifically today. We can never directly observe what's inside beyond the horizon's veil completely. Spinning black holes create a unique region that non-spinning ones don't have at all. This region is called the ergosphere, and it sits just outside the event horizon. Inside the ergosphere, space itself rotates around the black hole unavoidably and constantly. Nothing can remain stationary relative to distant stars, no matter how it tries. Everything gets dragged around in the direction of the black hole's spin necessarily. This creates one of the strangest regions in all of physics today. The ergosphere exists because spinning mass drags space-time around with it as it rotates. Einstein's equations predict this frame dragging effect from rotating matter distributions everywhere. Upiliège code 90 allow fict 400 derived. Batange scene. When Haring satellites orbiting Earth experience frame dragging, but it's extremely subtle and weak. Near spinning black holes, frame dragging becomes enormously strong and dominant completely. So strong that it creates this distinct region with unique properties unlike anywhere. The ergosphere's inner boundary is the event horizon itself that we discussed earlier. Its outer boundary is called the static limit, or ergosurface by physicists. Between these two surfaces lies the ergosphere region where strange things happen. The static limit sits farther from the center than the horizon does. At the poles, it touches the horizon exactly at the same location. At the equator, it bulges outward to nearly twice the horizon radius. This bulging shape comes from the centrifugal effects of the black hole's rotation. Rotation creates outward pressure that counteracts gravity's inward pull partially at equator. This pushes the static limit outward farther at the equator than poles, creating an oblate spheroid shape that's flattened at both poles significantly. The faster the black hole spins, the more pronounced this equatorial bulge becomes. Inside the ergosphere, remaining stationary becomes physically impossible under any circumstances whatsoever. Space itself is rotating so fast that standing still would require moving. Faster than light, speed relative to the rotating space around you. Since nothing can exceed light speed, standing still becomes impossible completely, period. Everything must rotate with the black hole, whether it wants to or not. Even light gets dragged around inside the ergosphere significantly and measurably always. Light beams can't travel straight through this region without being pulled sideways. They spiral around the black hole while also moving outward or inward, creating complex, curved paths through the ergosphere's rotating space-time structure completely. This makes the ergosphere act like a cosmic whirlpool of space itself. Objects can still escape from the ergosphere, unlike inside the horizon itself. You can enter the ergosphere, experience its effects, then exit successfully to safety. This makes the ergosphere very different from the event horizon fundamentally in nature. The horizon is a point of no return, but the ergosphere isn't. It's a weird region you can visit and leave, taking experiences back. This escapability enables something called the Penrose process to extract energy efficiently. Named after physicist Roger Penrose, who discovered it theoretically in the 1970s. The process works by splitting an object into two pieces inside the ergosphere. One piece falls into the black hole, while the other escapes outward. If done correctly, the escaping piece has more energy than the original had. The extra energy comes from the black hole's rotational energy being tapped. This is the only known method to extract energy directly from a black hole. By stealing from its rotational energy reserves stored in the spin itself. Each time this happens, the black hole spins down slightly more slowly. Eventually, a black hole could be spun down completely to non-rotating state. Though this would take enormous amounts of time in practice, realistically speaking, advanced civilizations might someday use the Penrose process as an energy source, orbiting near the ergosphere and extracting energy from black hole spin repeatedly. This could provide essentially unlimited power for billions of years potentially forward. The black hole would slowly spin down, but remain a black hole, just a non-rotating one eventually, after all the spin energy was extracted. The ergosphere also creates powerful jets from some black holes we observe today. Matter falling into the ergosphere gets accelerated to tremendous speeds by the rotation. Some of this matter gets funneled along the rotation axis toward the poles, emerging as narrow beams shooting outward at nearly light speed incredibly fast. These jets can extend for millions of light years out into intergalactic space. The exact mechanism creating these jets isn't fully understood yet by scientists today. But the ergosphere's frame dragging clearly plays a crucial role in their formation. Magnetic fields threading through the ergosphere get twisted by the rotation severely. These twisted magnetic fields can accelerate charged particles to extreme energies observed, launching them outward along the rotation axis in focused beams we detect. Frame dragging in the ergosphere affects particle orbits in complex ways measurably today. Particles orbiting prograde with the spin stay closer to the black hole than expected. Frame dragging helps them maintain orbits at smaller radii than otherwise possible. Particles orbiting retrograde against the spin must orbit farther out instead necessarily. Fighting against frame, dragging requires larger radius to maintain stable orbital motion. This creates two different innermost stable circular orbits for spinning black holes entirely. One for prograde orbits, and one for retrograde orbits at different positions. The difference between them tells us about the black hole's spin rate accurately. By observing where these orbits occur in actual astronomical objects observed today, we can measure how fast supermassive black holes are actually spinning currently. The ergosphere stores enormous amounts of rotational energy in its structure itself. For maximally spinning black holes, up to 29% of total mass could theoretically be extracted as usable energy through Penrose process repeatedly. This is far more efficient than nuclear fusion, which converts less than 1% of mass into energy, even in the most efficient reactions possible. The ergosphere represents the universe's most efficient potential energy storage mechanism known. Time also behaves strangely in the ergosphere due to frame dragging effects present. Time not only slows from gravity like outside, it also rotates with space, following spiral paths through space-time rather than straight lines forward in time. This creates closed time-like curves, theoretically, in some cases mathematically shown. Paths through space-time that loop back to their own past, potentially allowing time travel. Though these are probably unstable and couldn't actually be used practically speaking. The ergosphere's properties change with the black hole's spin rate directly and proportionally. Faster spin creates larger ergosphere with stronger frame, dragging effects throughout. Slower spin creates smaller ergosphere with weaker effects that are less dramatic. Non-spinning black holes have no ergosphere at all, just the event horizon alone. This makes spin a crucial property, determining black hole behavior and characteristics. Measuring the ergosphere's size tells us the black hole's spin accurately through observations. By studying matter orbiting in and around the ergosphere carefully with telescopes, we map how frame dragging affects orbital motion in measurable ways today. This reveals the spin rate, even though we can't see the black hole. The ergosphere's effects on surrounding matter give it away clearly to observers. The ergosphere represents one of general relativity's most exotic predictions that came true. Frame dragging was predicted theoretically long before being observed in any context. Satellites around Earth barely measure it even with precise instruments available today. But around black holes, it becomes the dominant effect that can't be ignored. The ergosphere proves Einstein right about rotation, dragging space-time around with it. In the most extreme and dramatic way possible anywhere in the universe. Most black holes are surrounded by swirling disks of matter spiraling inward gradually. These accretion disks are among the brightest objects in the entire universe. They emit more light than entire galaxies, despite being relatively small in size. The disk forms when matter falls toward the black hole from surrounding space. Instead of falling straight in, the matter has angular momentum from its motion. This makes it spiral inward gradually, while orbiting the black hole repeatedly. The matter in accretion disks comes from various sources depending on the situation. Around stellar mass black holes, it often comes from a companion star nearby. The black hole's gravity pulls gas off the companion star's outer layers. This gas falls toward the black hole, but retains the orbital motion. Around supermassive black holes in galaxy centers, matter comes from everywhere in the galaxy. Stars that wander too close get tidally disrupted completely into gas streams. Gas clouds drifting through the galactic center get captured by black hole's gravity. As matter spirals inward through the disk, it moves faster and faster. Closer to the black hole means faster orbital velocity required to maintain orbit. This velocity difference between neighboring regions creates friction between them unavoidably and constantly. Gas at different radii rubs against gas at other radii continuously. This friction converts orbital kinetic energy into heat very efficiently over time. The heat generated by friction makes the disk extremely hot throughout its structure. Inner regions closest to the black hole reach millions of degrees temperature. Outer regions are cooler, but still thousands of degrees hot typically throughout. This tremendous heat makes the disk glow brightly in various wavelengths of light. The emission spectrum depends on the temperature at each location in the disk. The inner disk regions emit X-rays and ultraviolet radiation from extreme temperatures there. Middle regions emit visible light that our eyes could theoretically see directly if close. Outer regions emit infrared and radio waves from cooler temperatures present farther out. By observing the disk at multiple wavelengths, we map its temperature structure clearly. This tells us about the black hole's mass and spin rate precisely. The disk is quite thin, vertically compared to its radius extending outward horizontally. Typically only a few thousand kilometers thick, but millions of kilometers wide across. This thinness comes from gas settling into the orbital plane over time naturally. Vertical motion gets damped out by collisions, while orbital motion gets amplified instead. Eventually, the disk becomes a thin pancake shape, orbiting the black hole stably. Inside the disk, gas particles constantly collide with each other at high speeds. These collisions randomize the gas particles' velocities and create pressure within the disk. Pressure provides support against gravity, trying to compress the disk vertically thinner. This balance between pressure and gravity determines the disk's thickness everywhere present. Hotter regions have more pressure and are thicker proportionally than cooler regions. Magnetic fields thread through the accretion disk in complex patterns we're studying today. These fields come from the gas itself, which contains charged particles. Moving charged particles generate magnetic fields according to electromagnetic theory. These fields can become tangled and amplified by the disk's differential rotation, eventually becoming strong enough to affect the gas motion significantly in return. The magnetic fields can transport angular momentum outward through the disk efficiently over time. This allows matter to lose angular momentum and spiral inward more easily. Without this mechanism, the disk couldn't efficiently accrete onto the black hole. Matter would just orbit forever without falling in at all, realistically speaking. Magnetic fields solve this problem by redistributing angular momentum outward through turbulence. Turbulence in the disk creates fluctuations in brightness we observe from Earth clearly. The X-ray emission varies on timescales from milliseconds to years, depending on processes. These fluctuations tell us about conditions in the inner disk near the black hole. How fast matter is falling in, how dense the gas is there, all revealed through careful analysis of the brightness variations over time observed. The innermost part of the disk reaches the innermost stable circular orbit. This ISCO marks where stable orbits end and plunging region begins inward. Inside ISCO, matter no longer orbits but falls straight into the black hole. This plunge happens very quickly, in just milliseconds typically for stellar mass holes. The matter disappears from view as it crosses the event horizon finally. The disk's inner edge at ISCO is quite bright from hot gas there. This creates a bright ring in images of black holes we've taken recently. The famous image from 2019 showed this bright ring clearly around darkness. The ring's size and shape tell us about the black hole's properties accurately. Comparing observations to theoretical models reveals mass and spin rate precisely measured. Some accretion disks are thick and puffy rather than thin pancakes instead. These thick disks occur when accretion rate is extremely high and powerful. The disk puffs up from radiation pressure, pushing outward from within strongly, creating a geometrically thick disk that looks different from thin disk versions. These thick disks emit differently and are less efficient at radiating energy away. The dividing line between thin and thick disks is called the Eddington limit. This is the maximum rate at which matter can accrete onto a black hole. Above this rate, Radiation pressure pushes matter away, preventing further infall temporarily. Below this rate, matter can accrete steadily in thin disk configuration stably. Most black holes accrete below Eddington limit most of the time observationally confirmed. Accretion disks can be incredibly stable, lasting for millions of years steadily. The disk around our galaxy's central black hole has persisted for extremely long times, though it's currently quite faint because little matter is falling in currently now. Other black holes have much brighter disks from active feeding happening now. These differences tell us about the environment surrounding each black hole uniquely. The disk also acts as a cosmic laboratory for physics under extreme conditions. Some black holes produce narrow beams of matter and energy called jets. These jets shoot outward from near the black hole at nearly light speed. They can extend for millions of light years through intergalactic space incredibly far. Jets are among the most powerful and energetic phenomena in the entire universe. They carry enormous amounts of energy away from the black hole into surrounding space. Jets appear to emerge from the black hole's rotation axis at the poles. One jet shoots out from the North Pole, another from the South Pole. They're highly collimated, meaning they stay narrow over huge distances traveled. This collimation requires strong magnetic fields to confine the jet material tightly. Without magnetic confinement, the jets would spread out and dissipate quickly into space. The exact mechanism creating jets isn't fully understood yet by scientists researching them. But we know magnetic fields play a crucial role in their formation definitely. Magnetic field lines thread through the accretion disk surrounding the black hole. These fields get twisted and amplified by the disk's rotation over time. Eventually, they become strong enough to launch material outward along the rotation axis. The ergosphere likely contributes to jet formation, as well through frame, dragging effects. Frame dragging twists magnetic fields more efficiently near the black hole's poles. This twisted field can extract rotational energy from the black hole itself directly, converting spin energy into kinetic energy of particles shot outward in jets. This makes jets incredibly efficient at tapping the black hole's energy reserves continuously. Jets contain charged particles, mostly electrons and protons moving at relativistic speeds. These particles spiral around magnetic field lines as they travel outward. This spiral motion makes the particles emit synchrotron radiation we can observe. The radiation spans from radio waves to X-rays depending on particle energies. By observing jets at different wavelengths, we map their structure and properties. The particles in jets are accelerated to tremendous energies we can barely achieve. Some particles reach energies millions of times higher than particle accelerators produce. We don't fully understand how this acceleration happens so efficiently in jets. Likely magnetic reconnection events provide additional energy boosts to particles repeatedly. Or shock waves traveling through the jet accelerate particles at their fronts continuously. Jets can be steady and continuous, or intermittent and variable over time instead. Some black holes produce steady jets that don't change much over years. Others produce jets that flicker and vary on short timescales observationally. These variations might come from instabilities in the accretion disk feeding material, or from changes in the magnetic field configuration near the black hole itself. When jets plow into surrounding gas, they create huge bubble structures we observe. These bubbles can be larger than entire galaxies, millions of light years across. The jet's energy inflates these bubbles like cosmic balloons over millions of years. Inside the bubbles, the gas is hot and diffuse, glowing faintly in radio waves. These radio lobes are common around galaxies with active supermassive black holes present. Jets affect the evolution of galaxies, hosting the black holes significantly over time. They inject energy into surrounding gas, heating it up substantially throughout regions. This heating can prevent gas from cooling and forming new stars efficiently, acting as a kind of thermostat regulating star formation rates in galaxies. Without jets, galaxies might form stars too rapidly and quickly exhaust their gas. This jet feedback is now believed to be crucial for galaxy evolution overall. It explains why the most massive galaxies stopped forming stars efficiently. Their supermassive black holes grew large and produced powerful jets as a result. These jets heated the surrounding gas and shut down star formation effectively, creating the massive dead galaxies we observe today with little gas remaining. Jets also enrich intergalactic space with heavy elements from processed material ejected. Gas near the black hole gets processed through nuclear reactions before ejection. This enriched material spreads through intergalactic space carried by jets outward, eventually mixing into new gas clouds that form new stars later. This recycles elements and distributes them across cosmic scales over time. Some jets produce spectacular light displays visible across the entire electromagnetic spectrum. The jet from the galaxy M87 is particularly famous today. It extends for thousands of light years from the galaxy's core outward. We can see individual knots of bright emission moving along the jet. These knots are probably shock waves or magnetic structures traveling with the flow. Relativistic beaming makes jets appear brighter when pointed toward us than away. If the jet points toward Earth, particles moving near light speed appear boosted. Their light gets beamed forward in our direction, making them appear brighter. If pointed away, the opposite happens and the jet appears much dimmer. This beaming effect creates observational biases in how we detect jets from Earth. Jets also produce high-energy cosmic rays that bombard Earth from space constantly. These cosmic rays are charged particles traveling at nearly light speed through space. Some come from supernova explosions, but jets contribute significantly to cosmic ray population. The highest energy cosmic rays might come exclusively from jets actually today, where particles get accelerated to energies we can't explain any other way. Studying jets helps us understand particle acceleration mechanisms under extreme conditions completely. How magnetic fields and shocks can accelerate particles so efficiently to extreme energies. This has applications beyond black holes to other astrophysical contexts as well. Supernovae, pulsars, and other energetic sources likely use similar acceleration mechanisms observed. Jets represent one-way black holes, give energy back to the universe, instead of just consuming everything that falls in without return or output. The black hole launches some material back out in powerful jets effectively. This creates a balance between feeding and feedback that shapes cosmic structure, making black holes active participants in galaxy evolution rather than just passive sinks. The study of jets continues to be an active research area today. New telescopes with better resolution are revealing finer details than ever before. We're seeing jet launching regions closer to black holes than previously possible. This will help us finally understand how jets form and what powers them, solving one of astrophysics' long-standing mysteries about these incredible cosmic phenomena. When stars wander too close to supermassive black holes, they can be destroyed completely. The black hole's gravity pulls harder on the near side than the far side. This difference in gravitational pull is called a tidal force stretching things apart. If strong enough, tidal forces can overcome the star's self-gravity holding it together. The star gets stretched into a long stream of gas flowing around the black hole. This violent death is called a tidal disruption event by astronomers studying them. Tidal forces exist whenever gravity changes strength over distance in space anywhere. Earth feels tidal forces from the moon pulling on our oceans, creating tides. The near side of Earth feels stronger pull than the far side measurably. This difference is small enough that Earth stays intact without being torn apart. But the principle is the same as what happens near black holes dramatically. The distance where tidal forces become strong enough to disrupt stars depends on factors. The black hole's mass is most important, with more massive holes disrupting farther out. The star's size and density also matter, with larger stars disrupted farther away. For typical stars like our Sun, near supermassive black holes centrally located, tidal disruption occurs at distances of about 1 astronomical unit approximately measured. That's roughly the distance between Earth and the Sun for comparison purposes. Stellar, mass black holes can't tidally disrupt stars in the same way effectively. Their tidal disruption radius lies inside the event horizon for typical stellar masses. The star would cross the horizon before tides could tear it apart completely. It would just disappear into the black hole intact without disruption happening first. Only supermassive black holes can create observable tidal disruption events astronomically today. When a star enters the tidal disruption radius, stretching begins progressively and dramatically. The star elongates into an elliptical shape first, before further stretching occurs. Then, it stretches into a cigar shape as tides grow stronger approaching closer. Eventually, the star is pulled into a long, thin stream of gas streaming around. The stream can be millions of kilometers long, but only thousands wide comparatively. About half the stream's gas has enough energy to escape the black hole. This gas flies away into space at high velocity, lost to the black hole permanently. The other half doesn't have enough energy to escape and falls inward instead. This gas has angular momentum, making it orbit rather than fall straight in. It forms an accretion disk around the black hole very rapidly over time. The newly formed accretion disk is initially very bright from the violent disruption. The infalling gas heats up from friction and shocks, compressing it tremendously. This creates a bright flare visible across huge distances in multiple wavelengths. The the flare rises to peak brightness over weeks to months typically observed, then fades gradually over months to years as gas gets consumed steadily. We've observed dozens of tidal disruption events from galaxies across the universe today. They appear as sudden brightening in previously quiet galaxy centers where black holes lurk. The brightening follows predictable patterns that match theoretical models accurately developed. This confirms our understanding of tidal disruption physics is fundamentally correct overall. These events are rare in any given galaxy, happening perhaps once per 10,000 years. But the universe contains billions of galaxies, so we observe several events yearly. This gives us statistical sample to study how often they occur typically, and how their properties depend on black hole mass and other factors involved. Tidal disruption events provide unique opportunities to study supermassive black holes in detail. Many supermassive black holes are normally dormant and dark without active feeding occurring. But a tidal disruption lights them up temporarily, revealing their presence clearly today. This lets us find and study black holes we wouldn't otherwise know existed there. The events also probe regions very close to the event horizon precisely and carefully. The accretion disk from tidal disruption can extend down to the ISCO radius. Emission from this region is affected by strong gravity's effects, measurably so. By studying emission carefully, we learn about space-time near the event horizon. Testing general relativity in the strong field regime where it predicts extreme effects. Different types of stars produce different disruption events observationally with distinct signatures. Sun-like stars produce typical disruption events with standard properties we calculate theoretically. Giant stars disrupt farther out and produce more luminous events overall comparatively. White dwarf stars are more compact and disrupt closer in with different characteristics. Each star type reveals itself through the disruption event's observable properties uniquely. Sometimes, the tidal disruption produces jets shooting outward from the black hole. Only about 1% of disruptions produce jets that we've observed statistically. The reason for this rarity isn't well understood yet by scientists studying them. Perhaps it requires special magnetic field configurations that rarely occur naturally there. Or perhaps it depends on black hole spin in ways we don't understand yet. The tidal stream from disruption wraps around the black hole multiple times initially, creating a complex structure that eventually settles into a disk configuration stably. During the settling process, the stream can collide with itself violently at times. These self-collisions produce additional emission and energy release we sometimes observe happening, making the light curve more complex than simple models would predict occurring. Some disruption events might produce gravitational waves detectable by our instruments potentially, if the star is massive enough and black hole spins appropriately aligned together. The disruption process could emit gravitational waves at frequencies we can detect. So far, we haven't detected any gravitational waves from disruptions confirmed yet. But future detectors with better sensitivity might succeed in this endeavor eventually. Tidal disruption events also enrich the surrounding environment with heavy elements processed inside. The destroyed star contained elements created by nuclear fusion throughout its lifetime. These elements get spread around by the disruption into surrounding gas clouds. contributing to the chemical evolution of the galaxy over cosmic timescales. This recycling of stellar material is an important process in galaxy evolution. Some stars might survive a close pass and escape back out relatively intact. These partial disruptions strip away outer layers, but leave the core intact. The star loses mass, but survives to continue its life afterwards somewhat, though it's been forever changed by the encounter with the black hole dramatically. These partial disruptions might be more common than full disruptions actually occurring. The tidal disruption zone represents a dangerous region around every supermassive black hole present. Stars wandering into this zone risk destruction from overwhelming tidal forces experienced. This clears out stars from the immediate vicinity of black holes over time, creating a relatively empty region right around supermassive black holes in galaxy centers. Though new stars constantly wander in to replace those destroyed earlier continuously. Supermassive black holes don't just affect their immediate surroundings, but entire galaxies. Their gravitational influence extends across thousands of light years from the center outward. This creates a sphere of influence where the black hole's gravity dominates. Within this sphere, stars orbit the black hole more than the galaxy itself. This gives the black hole control over stellar motions and dynamics present. The sphere of influence radius depends on the black hole's mass, directly proportional. More massive black holes have larger spheres of influence extending farther outward. For the Milky Way's black hole of 4 million solar masses total, the sphere of influence extends about 3 light years from the center approximately. For the most massive black holes of billions of solar masses instead, the sphere can extend for hundreds of light years outward from center. Within the sphere of influence, stars orbit in randomly oriented elliptical orbits. Outside the sphere, stars orbit in the galaxy's disk plane, primarily organized. This transition marks the sphere's boundary clearly in observations we make today. By measuring stellar orbits, we map the sphere of influence precisely and accurately. This reveals the black hole's mass, even though we can't see the hole. The black hole's gravity prevents stars from getting too close to center ultimately. Stars that approach too closely either get tidally disrupted, as discussed earlier, completely, or they get flung outward at high velocity from gravitational slingshot effects. This creates a hollow core in the stellar distribution right at center, a small region relatively empty of stars immediately surrounding the black hole itself. This core has been observed in many galaxies, including our own Milky Way. The innermost region contains far fewer stars than would be expected normally. This confirms the black hole's disruptive influence on stellar dynamics there clearly. The core size correlates with black hole mass across many galaxies observed. Bigger black holes create larger cores depleted of stars in their centers. The black hole also affects star formation in the galactic center region significantly. Tidal forces and strong gravity make star formation more difficult there generally. But sometimes, the black hole's influence can actually trigger star formation too, by compressing gas clouds through tidal forces or shocking them with outflows. This creates complex star formation patterns near galactic centers we observe today. The black hole's mass correlates with galaxy properties in surprising ways discovered. larger black holes are found in more massive galaxies with more stars. This relationship is called the black hole galaxy mass relation by astronomers today. It suggests black holes and galaxies evolved together through cosmic history, each influencing the other's growth and development over billions of years' time. This correlation wasn't expected theoretically when first discovered in observations, surprisingly. The black hole is tiny compared to the galaxy, less than a billionth of the galaxy's total mass, typically in most cases we observe. Yet, somehow, the black hole's mass is precisely related to galaxy mass. This implies they communicate and regulate each other's growth, somehow coordinated. Feedback from the black hole is thought to explain this relationship today. As the black hole feeds and grows, it produces outflows and jets. These outflows heat gas throughout the galaxy, preventing star formation from proceeding. This regulates galaxy growth by limiting how many stars can form. The galaxy and black hole grow together until feedback balances feeding precisely. At this point, both stop growing and the relationship is established firmly. This feedback mechanism is now included in galaxy formation simulations routinely today. Without it, simulated galaxies grow too large and have too many stars. With feedback included, simulations match observations much better across scales observed. This confirms feedback from black holes is crucial for understanding galaxy evolution. They're not just passengers, but active drivers of how galaxies develop. The black hole also creates a gravitational potential well at the galaxy center. This potential well helps hold the galaxy together against disruption from outside forces. It stabilizes the central region and keeps stars orbiting there bound tightly together. Without this central concentration of mass, galaxies might be less stable structurally. The black hole acts like a gravitational anchor holding things together centrally. Over cosmic time, black holes grow by accreting gas and merging with others. When galaxies merge together, their black holes eventually merge too ultimately. This adds mass to the black hole and can trigger episodes of activity. As gas gets funneled toward the center during the merger chaotically happening. This creates the brightest quasars we observe in the early universe clearly. Quasars are galaxies with supermassive black holes feeding extremely rapidly and powerfully. They're so bright they outshine their entire galaxy of hundreds of billion stars. All that light comes from the accretion disk around the black hole glowing. Quasars were much more common in the early universe than today observationally confirmed, suggesting black holes were growing more rapidly then through mergers and accretion. Today, most supermassive black holes are quiet and dormant with little feeding occurring. Our Milky Way's black hole accretes only tiny amounts compared to its maximum, creating weak emission barely detectable with our best instruments available today. This suggests black holes and galaxies reached an equilibrium state currently present, where feedback balances feeding and both have stopped growing significantly now. The relationship between black holes and galaxies is still being studied intensively. We're discovering new aspects of how they influence each other constantly. Future observations with better telescopes will reveal finer details than possible today, helping us understand this cosmic dance between black holes and galaxies better, and how it has shaped the universe we see around us currently. When black holes merge together violently, They create ripples in space-time itself. These ripples are called gravitational waves and travel at light speed. They stretch and squeeze space itself as they pass through regions. We can now detect these waves with specialized instruments on Earth successfully. This has opened a completely new way to study black holes directly. Gravitational waves were predicted by Einstein in 1915 theoretically first. His general relativity equations showed accelerating masses should create waves naturally. But he thought they'd be too weak to ever detect, practically speaking. For almost a century, this prediction went unconfirmed by observations anywhere. Until finally, in 2015, we detected gravitational waves directly at last. The detection came from LIGO, the Laser Interferometer Gravitational Wave Observatory specifically. Two detectors in different locations simultaneously detected the same signal passing through. The signal came from two black holes merging over 1 billion light-years distant. Each black hole was about 30 times our Sun's mass approximately measured. They spiraled together and merged into one black hole, ultimately combined. The gravitational wave signal has a characteristic shape called chirp by scientists. It starts at low frequency as the black holes orbit far apart. As they spiral closer, the frequency increases gradually but steadily upward. At merger, the frequency peaks and amplitude maximizes dramatically and suddenly. Then it rings down as the final black hole settles into stable configuration. This ring-down phase is particularly interesting because it reveals black hole properties directly. Every black hole rings at specific frequencies determined by its mass and spin, like a bell ringing at specific notes determined by its shape. By measuring ring-down frequencies, we determine the final black hole's properties precisely. This tests Einstein's predictions about black holes in extreme gravity conditions. So far, every detection has confirmed general relativity's predictions perfectly without deviation. The masses, spins, and ring-down frequencies all match theoretical expectations, precisely calculated. This gives us great confidence that we understand black holes correctly fundamentally, at least in the regime we can currently observe with instruments available. Gravitational waves carry information about the merger process itself happening dynamically there. How the black holes spiral together over time in their final moments. How much energy was released as gravitational waves during the merger itself. And how the final black hole formed from the merger of two predecessors. All of this is encoded in the gravitational wave signal we detect. The energy released in gravitational waves is truly staggering in magnitude completely. A typical black hole merger releases energy equivalent to several solar masses. Converted entirely into gravitational waves over just a few seconds of time. This is more power than all the stars in the observable universe, combined during those brief moments of the merger happening dramatically there. Gravitational waves from black holes have specific polarizations that we can measure today. The waves stretch space in one direction while squeezing perpendicularly simultaneously. This creates a characteristic pattern that we can detect with our instruments precisely. The polarization depends on the orbital plane orientation relative to Earth's position. By measuring polarization, we learn about the binary's orientation in space. Multiple detectors around the world work together to triangulate gravitational wave sources. By comparing arrival times at different locations, we locate sources in the sky. This triangulation is how we determine which direction the waves came from, and help optical telescopes follow up and search for accompanying light emission. This multi-messenger astronomy combines gravitational and electromagnetic waves together for study. Black hole mergers happen more frequently than astronomers expected, originally thinking about them. We detect several mergers every month now, with current sensitivity levels achieved. This suggests black holes are common throughout the universe's history over time, and that binary black holes form and merge regularly across cosmic evolution. This was surprising because making black hole binaries isn't straightforward, theoretically speaking. Binary black holes can form through several different pathways astronomers propose today. Two massive stars born together might both become black holes eventually after evolution. Or black holes in dense star clusters might pair up through gravitational interactions. Or galaxies merging might bring their black holes together ultimately over time. Each pathway predicts different properties for the mergers we observe occurring. When something falls into a black hole, where does it go exactly and completely? Does it truly disappear from the universe forever without any trace remaining? Or does information about it somehow survive in ways we don't understand yet? This question has puzzled physicists for nearly 50 years of intensive research. It's called the black hole information paradox, and it remains unsolved today. The paradox sits at the intersection of quantum mechanics and general relativity, two theories that describe nature perfectly in their own domains separately, but clash dramatically when we try to combine them together near black holes. Quantum mechanics has a fundamental rule that information cannot be destroyed ever. Information here means all the quantum properties describing a particle's state completely. Its position, momentum, spin, charge, and every other measurable quantum property. According to quantum theory, this information must be conserved absolutely always, even when particles interact or transform into other particles through processes. The total information content of the universe must remain constant over time. When black holes merge together violently, they create ripples in space-time itself. These ripples are called gravitational waves and travel at light speed. They stretch and squeeze space itself as they pass through regions. We can now detect these waves with specialized instruments on Earth successfully. This has opened a completely new way to study black holes directly. Gravitational waves were predicted by Einstein in 1915 theoretically first. His general relativity equations showed accelerating masses should create waves naturally, but he thought they'd be too weak to ever detect, practically speaking. For almost a century, this prediction went unconfirmed by observations anywhere. Until finally, in 2015, we detected gravitational waves directly at last. The detection came from LIGO, the Laser Interferometer Gravitational Wave Observatory specifically. Two detectors in different locations simultaneously detected the same signal passing through. The signal came from two black holes, merging over 1 billion light-years distant. Each black hole was about 30 times our sun's mass approximately measured. They spiraled together and merged into one black hole, ultimately combined. The gravitational wave signal has a characteristic shape called a chirp by scientists. It starts at low frequency as the black holes orbit far apart. As they spiral closer, the frequency increases gradually but steadily upward. At merger, the frequency peaks and amplitude maximizes dramatically and suddenly. Then it rings down as the final black hole settles into stable configuration. This created a direct conflict between quantum mechanics and general relativity. Quantum mechanics absolutely requires information conservation without any exceptions ever allowed. General relativity plus Hawking radiation seemed to destroy information completely and permanently. One of these theories had to be wrong or incomplete somehow, but both theories work perfectly in every other situation we can test. The paradox suggested something fundamental was missing from our understanding completely. Physicists have proposed many different solutions to this paradox over decades. Each solution requires modifying our understanding of black holes or quantum mechanics, or sometimes both theories simultaneously in coordinated ways together necessarily. None of these proposed solutions has been conclusively proven correct yet, but they've led to fascinating insights about the nature of reality itself. One early proposal suggested information isn't destroyed but locked inside the black hole. Behind the event horizon, information still exists but is inaccessible to outside observers. When the black hole eventually evaporates completely at the very end, the information suddenly escapes all at once in the final burst. This preserves information conservation, but creates other problems with physics laws. The sudden information release would violate causality and local physics principles severely. Another idea suggested that information slowly leaks out in the Hawking radiation. Even though the radiation appears thermal, it might contain subtle correlations. These correlations encode information about what fell in originally over time. This requires the Hawking radiation to be more complex than originally calculated, with quantum entanglement between early and late radiation particles creating connections. This idea is called black hole complementarity and has many supporters today. The holographic principle offers a radically different perspective on this paradox entirely. It suggests that everything inside a black hole is encoded on the horizon. The two-dimensional surface of the event horizon contains all the information about the three-dimensional volume inside it in encoded holographic form, like a hologram encoding three-dimensional images on two-dimensional film surfaces. This means the inside might not even really exist as separate space, but is just a projection of information stored on the horizon surface. If the holographic principle is correct, information never really goes inside at all. It gets encoded on the horizon surface as things appear to fall. The apparent falling inward is just an illusion from one perspective viewed. From another perspective, everything is always on the horizon's surface encoded. This resolves the paradox by denying that information ever enters the hole. It stays on the horizon where Hawking radiation can gradually release it. Gerard II Hooft and Leonard Susskind developed the holographic principle in 1990s. It was inspired by studying black hole thermodynamics and entropy properties carefully. Black hole entropy is proportional to the horizon's surface area measured precisely, not to the volume inside as you might expect for normal objects. This suggested that the horizon's surface is what really matters fundamentally, and that it stores all the information in some encoded form. String theory provides mathematical support for the holographic principle's validity today. In string theory, black holes can be constructed from strings and branes. These constructions allow calculating black hole properties from first principles mathematically. The calculations confirm that information is preserved during black hole formation, and that Hawking radiation does carry information out encoded in correlations. This gives physicists confidence that information is indeed conserved after all. But string theory calculations work best for special theoretical black holes, with extra dimensions and supersymmetry that don't exist in our actual universe. Whether the same conclusions apply to real black holes remains uncertain today. We need a complete theory of quantum gravity to definitively resolve this. And we don't have that theory yet, despite decades of intensive effort. Another proposed solution involves modifying the event horizon's nature fundamentally itself. Maybe the horizon isn't a smooth surface, but has structure at tiny scales. This structure could release information gradually as things fall through it completely, or create a firewall of high-energy particles right at the horizon that destroys infalling information violently, but in a way that preserves it. These ideas are called firewall paradoxes and create their own problems with physics. The firewall idea emerged in 2012 from calculations by Almhiri and colleagues. They showed that preserving information conservation requires something radical at the horizon. Either the horizon isn't smooth, or quantum mechanics breaks down there somehow, or information can travel faster than light through quantum entanglement effects. Each option violates principles we thought were fundamental to physics itself. This made the paradox even more troubling than before to researchers. Some physicists think the paradox reveals that space-time is not fundamental, that space and time emerge from something deeper and more basic. At the black hole horizon, this emergence breaks down partially, revealing the underlying structure that creates space-time in the first place. This radical idea suggests we need to completely rethink space and time as approximate concepts rather than fundamental aspects of reality itself completely. Recent work on quantum entanglement has provided new insights into this question. Entanglement creates connections between particles regardless of their spatial separation in space. These connections might be related to space-time geometry in deep ways. Some calculations suggest that space-time geometry itself emerges from entanglement patterns. The geometry of space-time is quantum entanglement between different regions of space. This ER equals EPR conjecture connects black hole physics to quantum mechanics. If space-time emerges from entanglement, then black holes might work differently. Information falling in creates entanglement with the black hole's existing state. This entanglement stores information in the correlations between particles inside and outside. When Hawking radiation emerges, it's entangled with earlier radiation particles emitted. This entanglement gradually transfers information from inside to outside over time, preserving information conservation through quantum correlations spread over time periods. The ADES-CFT correspondence provides another mathematical framework for understanding this problem. This is a duality relationship discovered in string theory calculations, mathematically proven. It relates gravity theories in certain current field theories. living on the boundary of those spacetimes to Kiyotchiap theories. Living on the boundary of those spaced in this framework, black holes in the bulk correspond to thermal states. In the boundary theory where information is manifestly conserved always clearly. Since information is conserved in the boundary theory which is exactly equivalent to the bulk gravity theory including black holes that evaporate completely, information must also be conserved in the bulk theory as well. The black hole evaporation process in bulk corresponds to thermalization processes. In the boundary theory, where information conservation is obvious and straightforward, by studying populations of mergers, we learn which formation pathways are common. The distribution of masses and spins reveals how black holes formed originally. If masses cluster at certain values, that suggests specific formation mechanisms dominated. Current observations suggest multiple pathways are active, creating diverse merger population observed. No single mechanism explains all the mergers we've detected so far. Gravitational waves also let us study black holes that emit no light. Some black hole mergers happen in empty intergalactic space far from matter. These produce no electromagnetic emission at all, only gravitational waves detectable. Without gravitational wave detectors, we'd never know these mergers occurred anywhere. This reveals a hidden population of black holes we couldn't see otherwise. Future gravitational wave detectors will be even more sensitive than current ones. LIGO and Virgo are being upgraded to detect fainter signals from farther away. New detectors like Kagra in Japan and LIGO India are being built. And space-based detectors like ELISA will detect different frequency waves entirely. These improvements will let us detect thousands of mergers every year routinely. LISA will detect supermassive black hole mergers from early universe epochs specifically targeted, when galaxies were just forming and merging frequently throughout cosmic history. These mergers will reveal how supermassive black holes grew so massive observed, and how they influenced early galaxy formation and evolution over time. This will answer long-standing questions about the early universe's structure development. Gravitational waves might also reveal exotic objects beyond simple black holes potentially. Theoretical objects, like boson stars or gravastars, have different properties, measurably so. Their gravitational wave signatures would differ subtly from pure black holes in predictions. If we detect such differences, it would revolutionize our understanding of gravity, suggesting new physics beyond general relativity operates at extreme densities present. The detection of gravitational waves won Rainer Weiss, Barry Barish, and Kip Thorne the Nobel Prize in Physics in 2017 for their pioneering work leading it. It marked the beginning of gravitational wave astronomy as a new field, opening windows to the universe we couldn't access any other way possible, and confirming Einstein's century-old predictions in the most dramatic way imaginable today. Gravitational waves represent a new sense for observing the universe's violent events. Where electromagnetic waves are like sight, gravitational waves are like hearing effectively. Together, they give us a more complete picture of cosmic phenomena. This multi-messenger approach will dominate astronomy in coming decades moving forward, as we combine information from all available channels to understand the universe.